now we're going to turn it over to Ben Wolford-Lim, who's our senior developer at Allotrope, who's going to show a quick demo of what the ASMs actually look like.
Okay, so yeah, so we've talked about ASMs, kind of, where they came from, how they work, how they were built, but what do they actually look like? So we'll just do a little demo of what they look like and how you might use them. Right, so we've discussed the principles, as I said, but we'll take just a quick dive into a file to see how simple it really is. We're saying it's easy. Let's put our money where our mouth is. So for a little context, going back to Corey's earlier comment, typically data scientists, scientific researchers, people working with data to sort of explore the content of the data, like to use languages like Python, tools like Jupyter notebooks. That they're pretty commonplace. So in order to make this kind of a useful and fairly realistic example from that standpoint, we've put together a Jupyter notebook to look into an ASM, see how it works, and kind of give a little bit of flavor of what you can do with it, and to consider it the proverbial pot of gold at the end of the rainbow. Thanks, Vinny. This is a glimpse into the value that can be created when we start to create these ASMs at scale. If you have all of your data or most of your data in this kind of ASM format, then the reason for the journey together should hopefully become obvious when you see just how easy it is to use that data. So with that in mind, we'll just jump straight into a live demo. It's a Jupyter notebook. It's going to read, plot, and validate liquid chromatography ASM file. For those who want to give it a try, if you're interested in data science, the example notebook is available on our GitLab repository. The link is available in the slide deck, which will be shared after the conference ends. I could also paste it into the chat if people are interested in trying to follow along now. Or I can try to copy it into the chat, but of course in presentation mode that won't work, so maybe someone else can copy into the chat, and I'll just jump straight into the demo then. So hopefully it's actually showing the Jupyter notebook now. Again, I'm never quite confident with these video conferencing tools. They're doing what they say they do.
That's great.
Wonderful. So yeah, this is a Jupyter notebook. Again, for those who know data science, you probably have seen hundreds of these. For those who haven't, it's just a useful way of representing sort of text, data, images all in one file. You can literally run the code as you go, so you can very easily kind of put together, almost self-actuating reports in some regards. And it's a very common tool for data scientists, amongst other users, to sort of work with data. So first off, you can see that, as it's structured as an example. So there's text, there's also bits of code which we can run as we go. And first off, we'll run this bit of code, which is literally just pulling down the dependencies that you need to run this, and also doing some setup of a nice, pretty way of printing the data. I'll add for context that this chunk of code here is probably the largest single piece of code in the entire file. So, and this is just to make it look pretty. So that maybe gives you some indication as to how easy it really is to work with this. And I also have to say thanks to Corey for producing this, because he's the Python programmer. I just kind of put together the framework. He cleaned it up and made it all look pretty. But as I said, so you can run it in place. So if I hit the run button, what this does is pull down the dependencies, the things that you need. For context, for those who are familiar with data science and use this regularly, all of these are standard Anaconda includes. So I have an Anaconda installation, and all of this was already in place. I didn't have to download a single thing. Easy to run. So loads it up, just sets up a nice little tool to make it look pretty. So first off, we should get the file. So in this exercise, we're going to load it from our Allotrope Perl server, but of course, in the real world, you could load this from a REST endpoint. You could pull it out of S3, an Amazon data share, or any other file or Perl server, or anywhere really. It's just a file. So we'll just go ahead and pull this down, and Corey's nice little piece of code means that it presents this JSON file in a nice, fairly easily readable way. We can kind of expand it out and just take a look at the data. So I've opened it up a little bit. We have a liquid chromatography aggregate document. It holds a document, or some structure to provide a framework for storing all this information. The interesting bits is probably things like the sample document. We have underneath that, we have a sample identifier and a written name, so it's sample 1. We know that the analyst is JMR 38889. We have an injection document underneath that, which tells us information about the injection, the volume setting. So in this case, the injection was 5 cubic millimeters. The injection time's given there. So this was a 2016 example. We have information about the detector control settings. So in this particular example, we have 2 detector control documents. One of them is a single channel, and the other one, if I open up, is UV spectrum. So it allows storing of this kind of, different kinds of detections, different kinds of data sets, and all of these sort of settings can easily be stored. Again, this is all in line with our existing tabular model for liquid chromatography. It's just translated into an easy to read JSON format that hopefully looks pretty familiar for anyone who knows a bit about chromatography. It doesn't look particularly scary, at least that I hope not. So again, it's standard JSON. I didn't have to load any special packages or anything beyond sort of very, very standard kit, nothing Allotrope specific to pull this down and read it and represent it in a nice, easy way of understanding it. So we have some liquid chromatography data. That's great. How about we plot the chromatogram? Oh, I forgot to mention, yes, as well as all of this information here, the measurement document, we have the peak list and all the peaks, all this kind of data, and the one that's probably more relevant right now because we're about to use it is the data cube. So we have the chromatogram. It includes information on the structure, as Amnon mentioned. So it describes that what you're measuring is absorbance in milliabsorbance units, and you're measuring it against time, acquisition time in seconds, and I'll open it up once. It'll take a little bit of time because it is 36,000 entries, but it's the data. Here's the raw data right there. So you have the full chromatogram in the file. So if we have it, let's plot it. So again, we have a nice bit of code here, and immediately it pings it into a nice picture of a chromatogram. At least I assume it's a nice chromatogram. I have no idea what's being measured. I'm not a chromatographer, but it looks like a chromatogram to me. So it's also using this. So this plot is using pandas, which again, folks who use Python for data science will probably recognize that as a very common data science package in this context. So this data is, with very, very little work, a pandas data frame. You can immediately do some data science wizardry if you so wanted. In fact, most of the code that's on the screen here is not loading this data. It's making the labels correct based on the data set. So I spent more time putting together the labels than I did actually loading this into pandas. It really is that simple to work with. So we have the chromatogram. That's great if you want to work with the raw data. Easy. How about the peak table? So let's go ahead and do that, because most of the time you probably don't need the chromatogram. What you want is the peak table, and there it is. So in a nice pandas data frame, again, printed out as a table, we've got 3 peaks. They have peak areas, they have retention times, they have the units, and all the good stuff's there. So in really not very much code, not very much effort at all, we've got data, and more to the point, data in a nice, easily accessible format that people can just go ahead and work with in using standard existing tools, pandas, to do data science, or if you're doing something else, it's similarly easy to just load this in and do whatever you want to do with it. So we can load an ASM file pretty easily. We can read it and plot it pretty easily. The other step that Amnon mentioned earlier is validation. So we want to make sure that the data is correct. We don't want to be doing data science on bad data. So how about we validate it? So that's fine. That's easy, and we'll show you how to do that too. First off, we have to pull the Asm Manifest. As Amnon mentioned, there's one key attribute in the data, which is the Asm Manifest. What that does is basically, it's just a small file that tells you, as he said, where the adjacent schema can be grabbed from, what version of the ontology was used, what version of the shapes used. Most of this we don't need, but we do need to grab the schemas. So to do that, we need to grab the ASM manifest. And a key note, because this is something that we've hit for those that are interested in doing this, the code does this, but just in case you're writing your own code, you do need to send a request for JSON in the HTTP accept header when you request this, because if you don't specify, it will return turtle by default. That's just an artifact of how the Perl server was originally set up. Turtle is the default, and because there are two files identically named, the default is to pick turtle. Again, for those who are following along at home, the code already does this, but just in case anyone goes and writes this, that's something you might want to be aware of. Again, not particularly difficult to do. Very small piece of code here, and again, this half of this is just making sure that the right header's in place. But if we pull this down, we get a manifest, again, pulled straight from one of the Allotrop Perl servers. It lists the vocabulary, it lists the shapes, which we're not so interested in right now. And the main thing that we really care about is it lists the JSON schemas. So here's the link to the JSON schema that we're going to want to use. It pulls down the deconvoluted, the deconstructed version, not the embedded version, but that's fine. That's all we need right now, because we have a because the package that Python uses actually deals with references for us. So we'll stick with that one just to make it a bit easier to look at. So we pull down the manifest. We have a link to our schema. We can go ahead and pull that down now. Pull down the wrong cell. So if we go ahead and pull that schema from the file that we just got, it pulls down a JSON schema. Now this bit's probably going to look a bit more scary for those who aren't particularly familiar with JSON schema. Fortunately, for the use case that we're talking about here, for people who are doing sort of data scientists, sort of like people who are working just working with data in the lab, you don't need to understand or worry about this. You just need to be able to grab it and load it into your validator. It just works. This is the sort of secret sauce, as it were. You don't need to worry where it's coming from. Just pull it down and validate with it. That's where we come in to produce all of this. So again, for those who are comfortable with JSON schema, it probably doesn't look so bad. But again, your average data scientist doesn't need to look at this at all. You just pull it down. So we can go ahead and pull that down, and now we can use that to check that the data is correct. So we have the data, we pulled it earlier, we have the schema, we've just pulled that down. So let's go ahead and make sure that the data is actually valid. So we run that and the data is valid. Great. I'd hope the data is valid given it's our example code. But of course, we can say it's valid. That doesn't prove it's valid. Someone could just say, right, data is valid. That it's not a very convincing demo, unless you actually show that it doesn't work when it shouldn't work. So let's go ahead and break some things, make sure that it catches them. So we had a pump model number in the earlier file. That's a string. It's G7112B or something like that. How about we change that to a number? So then it's the wrong data type. So let's go ahead and try that and then validate it again. So it used to be 7112B, now it's 123456. And oh look, it's the wrong type. It's not a string. So the schema is not happy. We get a validation error. So if you're creating data that's wrong, has the wrong data type, it will tell you. How about if we give something the wrong unit? Because data types, it's an easy mistake to make, and sometimes an easy mistake to catch. But wrong unit, that's a little harder for a machine to understand, perhaps. So let's go ahead and try that. So we make a peak area unit seconds instead of milliabsorbent units, milliabsorbance units times seconds. So go ahead and change that. So the old peak area was milliabsorbance units, now it's seconds, and what do you know? It doesn't like that either. So the unit is wrong. It tells you exactly where it is. The peaks list, peak items. So you can find, with a little bit of effort, again, it helps when you refer back to the file, but you can find where the issue is and identify that, peak 0 had it wrong, effectively. So great, we can check that the units are correct, we can check that the types are correct. How about if we remove something that's important? So without sample identifier, you can't associate this data with what you're trying to measure. So sample identifier is a mandatory field in this. Let's take it out. So we go ahead and take it out. Used to have an identifier of 1938 4141. Now it doesn't, and it's missing. It's a required property, and it's not there. So again, the schemas work just like they did, just like they do on the shackle version, on the ADM version with RDF. We can check, things are present, things are absent. We can check that the units are correct. We can check the types are correct. All of the stuff is automatically generated from the schema tooling that we have to push from the RDF version into JSON schema, and that applies to all of our tabular models. We have these translations, we have these schemas available. That's really all it takes. In this, we've just pulled down a file, we've read the data, plotted the chromatogram, the peak table, we've tested the validation and made sure that it fails, works when it works and fails when it fails. All in that 10 minutes. Easy. I can say it, but hopefully those who do data science or use Python are nodding and agreeing. Maybe those who don't, might look at it slightly more askance. But it really isn't as complicated as you may fear. It really is that easy. It's not hard. So the last piece, which is slightly less technology and slightly more talky, is so we've read the data. We've plotted the results and we've validated whether it's right or wrong. The last piece, how do you find what the terms are and what the terms mean? And again, this is harking back a little bit to the talk I gave yesterday and to sort of one of Annon's earlier comments. If you're looking up terms, probably the easiest thing to do right now is to go to BioPortal, because all of these keys in the ASM file are the preferred labels from our ontology. You can just put them straight into the BioPortal search, go to the AFO page on BioPortal, jump to the term, the key in the file, and it'll plop you right out at the right term in the ontology with all of the details on the right hand side of the page about what the definition is, what the parent is, what that unique IRI is. All of these things should pop straight out from that. It's going to be by far the easiest way to take this file and look up anything that you're not sure of. If you're not quite sure if the term definition is exactly what you thought it was, or maybe the term wasn't quite how you thought it was, but we use preferred labels, but we also have synonyms, alt labels to sort of say other people call it this. Maybe the term wasn't exactly what you thought it was, but you can see that your term is in the alt label, then it's probably the right term you're after. And we just have a slightly different way of naming it in order to make sure that it's consistent and correct across all of our files and all of our techniques. So BioPortal, to basically find what the terms mean, is going to be one of the easiest ways to work. Of course, now we have the term dictionary, that may be an option, but as that's still in beta, we haven't included that in this file yet. We may update that as that becomes a sort of a fully finished and polished product. So yeah, hopefully in that sort of 10-ish minutes stint, I've shown you that it's pretty easy to work with our Allotrop simple model. It doesn't take much in the way of code, doesn't really take much in the way of sort of specialist skills. I mean, if you know a little bit about Python, a little bit about data science, and you've ever worked with a computer, pretty much, you can just pull this in and run it. It's really as simple as that. So, and with that, I think that's about it. So, any questions?
So actually, Ben, while you were talking, I retested it on the Google Colab environment, and it's a fully working version. So there is no need even for a workstation, just for a browser.
Even better. So yeah, you can load it into Google Colab and not have a local copy of Anaconda and Python. It really is a very low bar to get started. And this is just the Python example. Of course, you can use JSON in any language. It just shows how easy it is to get started. And for context, I'm not a Python developer. As I said before, Corey had to do a lot of cleanup and making things look pretty. But putting this together took half a day, and most of that was understanding how Python works. It's really, really easy to work with. The JSON is a very common format, and every language has libraries, and it's pretty easily structured to find what you want. So yeah.
Yeah, there's a question in the chat window. I don't know if you.
Yep, I see it. So Christian asks, thanks Ben for the live demo. ASM indeed looks very promising for our work in Python too. How do we actually get the ASM files? That's question one. And then two is there an ADF to ASM converter available already? So why don't we answer question 1 first?
Great. So getting the ASM files, it actually refers back to Amnon's talk earlier about looking into the GitLab repository. So the GitLab repositories have all of our models, which include the ASMs now. If you're looking for an instance file specifically, those are stored under the test folder. So we have GitLab, we have Perl and subfolders, and then we have a test folder. Underneath that, underneath that, you'll have the specific techniques, chromatography, conductivity, blood gas analysis, and so forth. And then underneath that, as you mentioned, the different maturity levels. Always go for the newest maturity level, obviously, because you're getting the very latest version. But at the bottom of that chain of folders, what you will find is technique name.json alongside the existing RDF versions of technique.adf and technique.ttl. So that's your instance artifact. The JSON schemas against that are in the JSON schema folder at that top level, and again follow the trail all the way down, conductivity 2021 12 rec and so on and so forth. Hopefully that answers where to find them, and I think Corey's already put the link to the GitLab repository in Perl. As for the ADF to ASM converter, we do have a tool that converts between ADF and ASM. Yes, that was part of the specification for the RFP. We wanted to make sure that bidirectional conversion was in fact correct and valid. So we do have a tool for that. I've got to double check what our release status on that is. I think it's in one of the accessible repositories, but I wouldn't swear to it, so I'd have to double check on that. But the intent is that yes, we will make that available. It does have a couple of caveats in that it's an automated translation for about 95% of our models, but there are a couple of edge cases that it cannot handle. So there are currently 2 models that it doesn't fully translate correctly. We can translate them, but there are manual steps at the end, which we have documentation for. So that converter is available. If it's not available to the community, it will be very shortly, but it is working and ready. So hopefully that answers that question too.
So I think for that one, I might have misspoke, but Christian was asking about converting here's where I misspoke, ADF, the allotrip data format, to the JSON allotrip simple models. So
Yes,
you just talked briefly on that aspect, right, of converting the different data instances.
That was what I was talking about. We have a tool to convert ADF files, data files, as in, here is a chromatography experiment result from ADF into ASM. But you're right, I should clarify, because ASM is built on the tabular models, this tool only applies for data in a tabular model form, and specifically an allotrep tabular model form. So for example, models which are in the graph form, so some of the LCUV examples, the mass spec examples, they do not have the they cannot be converted into an ASM at this point because the models are different, and so the translation does not work. It only works for the tabular models. But yes, in terms of converting ADF files into ASMs and back, that is now possible through that tooling.
Great. Thank you.